The next video from chapter 12 is going to go over angular velocity and acceleration, and this is all in chapter 12.2 of the textbook. Okay, so first off, last video we defined angular displacement. So now based on angular displacement, we can define angular velocity. And similar to how we defined translational velocity back in chapter 2, I think it was, we can start with an average angular velocity. And we're going to use the Greek letter omega, which looks kind of like a W, but it's a lowercase Greek omega to stand for angular velocity. And the average angular velocity is just the change in angular position, our angular displacement, theta final minus theta initial, divided by the time interval over which that happens. So delta theta over delta t. And just like we had with translational velocity, we can then define an instantaneous angular velocity. So once again, you imagine starting with the average angular velocity, and then you're going to take that delta t interval and shrink it so it's smaller and smaller and smaller and smaller and smaller. So you're averaging over a smaller and smaller time interval, and that defines a limit as delta t goes to 0. So it's the limit delta t goes to 0, delta theta over delta t, which hopefully you should recognize that's just the definition of a derivative. So it's the derivative of the angular position theta with respect to time, d theta dt. And just omega with no subscript stands for the instantaneous angular velocity. Now the SI units, well, remember our SI units for angular displacement are going to be radians, although remember that's not a real unit, but we still like to call it radians. Time is in seconds, so the SI units of angular velocity are going to be radians per second. Okay, so one thing I wanted to mention, so technically we can think of the angular velocity omega as a vector, so omega with the little arrow over it. And the way we define the direction of omega is with the right-hand rule. So imagine you have something that's spinning, right? So this is a little disk or something that's spinning in this direction. So the right-hand rule says that you take your fingers and you wrap your fingers in the direction of the rotation. So your thumb then gives the direction of omega. So although just a little side note here, so technically speaking, if you want to be real particular about it, the angular velocity is something known as a pseudo-vector since it doesn't actually transform as a true vector, but that's not going to be so important for us actually. Okay, so, and again, the thing to remember, so for omega, and for all of these, and for the angular acceleration too, which we'll get to next, so that the direction is always along the rotation axis, right? So we've got this spinning disk, and the rotation axis is straight up and down the way it's drawn in the picture. So the translation axis is along this post. So your direction of omega is always going to be along that post, so either pointing up or pointing down in this case. But the right-hand rule tells you which way it's going to be, right? So wrap the fingers in the direction of the rotation, thumb points in the direction of omega. Okay, so now we can define an angular acceleration. So, similar to what we did with just regular old acceleration back in chapter 2, so we can define an average angular acceleration. So for angular acceleration, we're going to use the Greek letter alpha. So there's kind of a tradition of using Greek letters for all this rotational stuff. So alpha is going to be our angular acceleration. So the average angular acceleration is the change in angular velocity, so omega final minus omega initial, divided by the time interval over which that happens. So average angular velocity is delta omega over delta t. And hopefully this should look a bit familiar to you, because if you remember, just regular old acceleration is delta v over delta t, while angular acceleration is delta omega over delta t. Okay, so then, just like we did before, we can then define an instantaneous angular acceleration. And again, you just imagine taking this delta t and taking the average over smaller and smaller time intervals. So you take the limit as delta t goes to 0, which defines a derivative. So alpha, our angular acceleration, is the time derivative of omega. And again, if you think about the units, well, omega is going to have units of radians per second. Then we're dividing by time, so it's radians per second, or radians per second squared. And again, so the direction is either going to be in the same direction as omega. So that happens, right, if omega is increasing, so your rotation is speeding up, or it's going to be in the opposite direction of omega if you're slowing down. But again, similar to what we had with omega, the direction of alpha is always going to be in the direction of the rotation axis, either pointing one way or pointing the other way.